Assalamu alaikum, lovely students. We're back with another video lesson. If you remember in the previous lesson, we were talking about centripetal force. And we talked about friction as a centripetal force, or when friction was the provider of centripetal force. And then, of course, we solved many questions regarding that. Today, we'll talk about the continuation of centripetal force, but before that, of course, we'll talk about rotational motion of an object. So what happens when an object, for example, pretend or assume that you are inside or sitting inside a car. The car moves in a straight line. So what happened when the car makes a sharp turn? Have this ever happened to you? For example, an object tries to go, let's say, in a straight line, yeah? And then the object, for example, goes in a straight line like this, and then it makes a sharp turn. But while it makes a sharp turn, it keeps sliding, for example, to the right, let's say. So the reason why does this happen, yeah? There is a force, of course, or in order to help you explain this better, we can call this the force that it feels like, if I say, it feels like there is a force that pushes you outward, let's say, or towards the door of the car. This force, of course, it is called centrifugal force, okay? But remember, this force is not a real force. It's just to help you explain what is happening while this happens. Okay, but the true reason behind this, or this phenomenon, can be explained like this. We can say, or this phenomenon can be correctly explained as this. Before the car enters the ramp, for example, or the corner, let's say the car moves in a straight line. So the car has a specific or certain moment of inertia, including you, because you would be part of the car, okay? But when the car makes a sharp turn, for example, so what happens? Now the direction of the motion is changed, but you, because you had a moment of inertia, and still, or we can say your moment of inertia tries to keep you on a straight line or moving in a straight line, just like before, even though you made a turn. So in this case, you would be pushed against, or you can say moved, of course, towards the door. So if the force of friction between you and the cushion, let's say, or the seat, if it is large enough, of course, it can keep you on the seat while the car makes a turn. But if the force of friction is not large enough, or not, let's say, big enough to keep you, let's say, or to change your direction, then of course you will be pushed towards the door, and then the door and the seat, of course, will provide enough centripetal force to keep you moving in a circular motion. All right, so we can say the phenomenon explains like this. Before the car enters the ramp, the passenger is moving in a straight line, as you can see. The car enters the ramp and travels along a curved path. So the passenger, meanwhile, because of inertia, tends to move along the original straight path. And of course, this movement is accordance with Newton's first law of motion, of course, which it says if an object is moving, it tends to, or it wants to keep moving. If it is stationary, it wants to stay stationary until an external force is acting on it. So of course we can say this movement we've mentioned is according to Newton's first law. So the origin of centripetal force is the force of friction between the passenger and the car seat. But if this force is not enough, then what will happen? If this frictional force is not sufficient to change your direction so that you can move in a circular path, then what will happen? Of course, you would be pushed against the wall, the door of the car. Then the door will, of course, provide big enough force to keep you in a circle. So we can say, if this force is not sufficient, the passenger slides across the seat as the car turns underneath. Eventually, the passenger encounters the door. So the door then provides a large enough force to enable the passenger to follow the same curved path, okay, as the car, of course. So what happens, or what do we learn from this? Remember, if you are moving in a straight line and then once you try to make a turn or let's say change your direction, of course, because of your moment of inertia, tries to keep you moving in a straight line or just as before, then of course you would be slightly moved, as you can see here. So the car turns or makes change the direction this way. Let's say it would be slight left, all right, in this case. But then if the if the force of friction between you and the seat is not large enough, then of course you'll be pushed against the door of the car, and then the door will provide enough force to keep you moving in a circular path. Okay, and then these questions, these are, we don't go through them, right? Now, the force that provides centripetal force. So, of course, so far, we've been mentioning so many situations where centripetal force or centripetal forces were provided, yeah? We said a string can, the tangent in a string can provide centripetal force. The elastic force of a spring can provide centripetal force. The gravitational force between the sun and the earth can provide centripetal force to keep the earth moving in an orbit, you can say, or in circular motion. And of course, friction is another one. So let's focus and see more situations where provided, or more forces that can be that can provide the centripetal force. So a car or a motorcycle making a turn on a horizontal surface. Remember, this is a horizontal surface we've mentioned before. So if you're moving horizontally and, let's say, driving your car on horizontal, let's say circular track, if you want to move in a circle, you need a centripetal force. But what provides the centripetal force? That is force of friction. So we can say the centripetal force provided will be the force of friction, or force of friction equal to the centripetal force, and then of course you can solve the questions. All right, the second, the rotation of the moon around the earth. Okay, so you can see here, now think about the rotation of the moon around the earth. There's no string, there's no connection. So what is the force that keeps the moon in orbit around the earth? That is gravitational force. So gravitational force would provide the centripetal force in this case. What about the rotation of the earth around the sun? Isn't that the same thing? Centripetal force, of course. Gravitational force provided or provides centripetal force, which is, of course, allows the earth to move in orbit around the sun. A bobsled, right, or a bobsled turning a corner on its track. So in this case, it's a little bit different. So, you know, like making a turn, and it is not on a horizontal surface, so it becomes something like a wall. So of course we can say normal force of the corner. Let's say we have a corner, okay? And of course this corner, let's say you're trying to move in this corner. Perhaps I cannot draw the exact shape that I wanted, but once you're making, let's say, a turn around a corner, of course you'll be like a little bit tilted. In this case, the normal force, perhaps some other terms would be the component of a normal force would provide the centripetal force needed. So normal force would be the centripetal force. A roller coaster's passengers are suspended upside down as it moves at a constant speed through a vertical loop, guys. So remember this. Let's say we have a roller coaster at a point here. You can see what provides the centripetal force in this case. And of course, we know that what are the forces that are downward? Of course, we know that the gravitational force is downward. And of course, normal of this track, you can say, here would also be downward in this case. So these two forces combined will provide the centripetal force needed for the roller coaster in order to be able to move in a circle. And then, of course, the cylinder of the amusement park, right? We did mention this one in the previous example, because it is a cylinder, so gravity will pull you down let's say because your back is against the wall of the cylinder, so your gravitational force is downward. What prevents you from sliding down is the force of friction, which is upward, but because your back is against the wall, so of course the wall pushes, pushes back on you, which is the normal force, and it is directed towards the center. So we can say in the cylinder of the amusement park, the centripetal force provided is provided by the normal force. And then the rotation of the electrons around the nucleus, and of course we know that this is electrical force, yeah? And of course electrical force or would be the provider for the centripetal force. And then a pilot making a turn on a horizontal altitude. Remember, whenever there is a horizontal altitude, of course we can say the net frictional force between the seat belt, and the passenger as well. Of course, remember this, a pilot making a turn on a horizontal. So it is not, let's say, the plane, it is the pilot, Okay, so in order, let's say the pilot is moving in a straight line, otherwise, let's say, and then in order for the pilot to make a circle or to move in a circle, of course, the seat belt, and of course, all this would provide enough friction in order for the pilot to be able to move in a circle inside the plane, of course. So the net frictional force between the seat belt, and of course the passenger, all this would provide the centripetal force in order to move in a circle. And then the next one is a bicyclist moving around a flat circular track. So now here, the situation is a bicyclist, remember this, the bicyclist will be on the bicycle, so the force of friction between the bicycle and the seat, and of course the pedal, all this would provide centripetal force for the bicyclist in order to be able to move in a circular path. So you can see the net force that, let's say, the bicycle seat, the pedals exert on the bicycle as well. So force of friction. A ball is attached to a citring. Whenever there is a citring and there is a movement that is in a, let's say, something moves in a straight line, of course, we can say tension would provide centripetal force. So we can say this, anything that is stretched, it has tension in it. So what if there is a ball attached to the end of a string and moves in or rolled in the air? Of course, now this string allows or makes the ball to move in a circle, and that is, so we can say tension is or provides the centripetal force. And then a ball is attached to a string, but this time moves in a vertical circular path at the lowest point. So at the lowest point, we can say, of course, centripetal force would equal to tension, let's say, tension force minus the gravitational force. And if I remind you of this, we had this, let's say, here's the string, let's say, right, and here's the ball. At the lower point, of course, we'll be moving in a circle, but at the lowest point here, let me redraw this one, okay, sorry. So here's the string, and here's the ball, and of course, this ball would be moving in a circle once it is rolled in the air. So you can see force of gravity is downward, tension is upward, yeah? And of course, we know that centripetal force is upward as well. So if you're willing to find centripetal force, then of course you will equal to tension minus gravitational force, as you can see over there. Okay, and remember, if you want to find tension force, of course, then you will have to add or move force of gravity to the other side, then tension equal to centripetal force plus the gravitational force. Or in another word, you can say tension has to be big enough, for example, to, let's say, counteract for gravity and also provide enough force for the object to move in a circle. So it has to be as big as both of these two. Okay, combined together. Now, for 12, we have, says a ball is attached to a string moving, we did mention, yes, a ball is attached, so that one, the other one was vertical, right? A ball is attached to a string moving, let's say, a vertical circular path at the highest point, and of course at the highest point, let's say force of centripetal force would be tension force plus gravitational force. So let's say here's the ball at the highest point, okay? Let's say this is the circle, gravitational force Fg is downward, of course, and then we can also say tension force, you can say also would be downward, yeah, because that is the case. So in this case, we can say centripetal force equals to tension force plus what? Plus Fg, of course. Okay, so these are basically, I can say, these are most of the forces that provide centripetal force, which I believe if you know these 12 forces, then this would be fair enough for you to solve all the questions related to that. Okay, now let's talk about Newton's law of universal gravitation. Now, remember, this part is very important, okay? And I'm trying to use simple language in order to help you understand better once and forever, hopefully, inshallah. All right, so take a look here. What do we have? Newton's first, or Newton's law of universal gravitation. Perhaps you've heard about, let's say, gravitational force, but what is the exact definition of gravitational force? Can we say gravitational force is the pull of Earth on an object? What do you say? No, right? So don't be, okay, so this definition, it would be incorrect because that is the definition of weight, yeah? The weight of an object equal to the gravitational pull of Earth on something, let's say, yeah? Or the gravitational pull of something. But here, when we say the gravitational, or the gravity, if I want to define gravity, gravity is a force. Of course, it exists between any two objects because of their masses. So you can look around between any two objects that you can use or you have. Of course, there is a force of gravity in between the two. For example, the force of gravity between this smart screen and of course this pen. Yeah, let's say between me and let's say the board. Yeah, but you might wonder, why don't we see the force of gravity? Of course, if the force of gravity were between objects that are small, you will not see the effect. So how can I define force of gravity? In a simple language, we can say force of gravity, it is the attraction force or the force of attraction that exists between any two objects because of their masses. So we can say the bigger the masses, the bigger the force of gravity. But there is one more thing which is included into this equation. Force of gravity is inversely proportional to the square of the distance between the two. I'll explain more, okay? So gravity, right, or gravitational force, we can say it is the mutual force of attraction between particles of matter. So there is a mutual force of attraction. So if there is something that, let's say, if I consider myself an object and consider something else an object, of course there is a force of attraction between us, yeah? That object would attract me, and of course I would attract the object in return as well. But remember, for example, like me and the Earth, yeah? And of course, if I make a jump, I would be pulled down by the Earth, yeah? Because there is a force of attraction between me and the Earth, yeah? Between you and the Earth. Okay, thank God this force is not it's not that big. Okay, so force of attraction, remember, the mutual force of attraction between particles of matter. So for example, we know that this is the moon and the Earth. There is a force of attraction between them, yeah? And can we say Fg equal to 9.81? No, of course not, yeah? So we have an equation to calculate the magnitude of the force of attraction between any two objects in the universe. So of course, or before that, we can say the gravitational force between the Earth and the moon is attractive according to Newton's second law. So we can say the force of attraction that is exerted by the Earth on the moon, of course, it is the same in magnitude to the force of attraction on the moon, let's say by the moon on the Earth, okay? But they have opposite directions, yeah? All right, so of course we can say Newton's law of universal gravitation states that every mass in the universe attracts every other mass with a force that is directly proportional to the product of their masses. Of course, remember this. So force of gravity is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. And of course we have a, let's say we have a constant, and this constant is called the constant of universal gravitation, or sometimes we just call it universal. That is a universal constant, which is called constant of universal gravitation. Before we move next, okay, remember Kepler was the one who suggested that planets revolve around the sun. Of course, before Kepler, scientists believed that Earth was the center of the solar system or the center of the universe, and every other thing were revolving around the sun, around the Earth, right? But Kepler proved them wrong. Of course, he said that no, right? Planets, including Earth, all of them, let's say, are moving in an elliptical orbit around the sun. Of course, and then even though scientists continued to believe that Earth was the center of the solar system until Sir Isaac Newton, of course, was able to derive, let's say, the elliptical path suggested by Kepler using the laws of motion. So remember this, we can say gravitational force, okay, is directly proportional to the product of the two masses and inversely, let's say, with the square of the distance between the two. So remember this, that is force of gravity. Okay, so based on this, we can say the bigger the masses, the bigger the force of gravity, okay? But then the bigger the distance between the two, then of course the less the gravitational force between the two. And there is something very important you need to know is that is the constant of universal gravitation. This universal gravitation has a value which is 6.673 times 10 to the power negative 11, and of course Newton meter square per kilogram square. This number, you need to know them, okay, or you need to memorize it. Once again, 6.673 times 10 to the power negative 11. What about the unit of this? So this unit, of course, it came in the exam perhaps multiple times, so try to remember. And even if you forgot, you can still use or find the unit using this equation. We know that Fg equals to universal constant or universal constant of universal gravity equals to m1, m2 divided by the radius square, yeah? Then of course, if you try to make this one the subject, then what will you get? You'll get force, right, times radius squared, and then divided by, let's say, mass times mass squared. This would be g, let's say. So we know that the unit of force is Newton, radius is measured in meters, so squared because it is squared, and these are the masses, mass times mass, or kilogram times kilogram is going to be kilogram squared. So you need to know this unit as well. Okay, so now what have we learned so far? Force of gravity or gravitational force exists between any two objects because of their masses. The bigger the masses, the bigger the force of gravity. The bigger the distance, the less the force of gravity. Okay, remember it is, sometimes we call it the inverse square law. That is because the radius is squared and it is inversely proportional with the force of gravity. So we have some notes here. These notes are very important. So the gravitational force is directly proportional to the product of the two masses, like we've mentioned. The bigger the mass, the bigger the force of gravity, which is, and also inversely proportional to the square of the distance between the two. So we can say force of gravity is inversely proportional with the distance between the two objects, but not just the distance, it is squared. Okay, next, Kepler suggested that Earth has an elliptical path, and of course Newton provided, let's say, proof for that. Okay, and then optical speed and period, these are cancelled. What does the gravitational force depend on? Yeah, that's a very good question. So we can say, by the way, this is, we can say, because this is a constant, yeah, so you can take this out of the equation. So what does the force or gravitational force depend on? So can we say it depends on the product of the two masses? Yes. Okay. Can we say it depends on the square of the distance between the two objects or the two masses as well? Yes. So we can say gravitational force depends on these two things, the product of the two masses and also the square of the distance between the two. Okay. And then Newton's law of universal gravitation, right? To determine the gravitational acceleration of a free fall on Earth, how do you find, or normally when we use the gravitational acceleration on Earth, we use g equal to 9.81. Where do we get 9.81? Okay, and of course we have, let's say, f or fg. If we want to use this, remember mass of the Earth is equal to 5.98 times 10 to the power 24 kilogram, and then radius of the Earth equal to 6.37 times 10 to the power 6 meter. Okay, so Fg, we can say force of gravity on Earth, let's say, equal to gravitation universal, right? Or the constant of universal gravitation equal to g. This would be the mass of the Earth, okay, multiplied by the mass of something, let's say my mass, okay? This question would be, for example, like to find the gravitational or my gravitational acceleration on Earth or any other object. So Fg equal to mass of the Earth multiplied by mass of the object, assume this is my mass, for example, and then divided by the radius squared, don't forget. So, but we know that Fg on Earth equal to mass times gravitational acceleration, correct? And then gravitational acceleration, of course, you know that, let's say, and then here's the, once again, g multiplied by mass of the Earth times my mass, so these two would cancel out, and divided by the radius squared. Now, if you plug the numbers into this, of course, this is what we're left with. G, we know that is 6.673 times 10 to the power negative 11, multiplied by the mass of the Earth was provided, which is 5.98 times 10 to the power 24 kilograms, and then divided by the radius, but remember the radius is square. So once you do all this, of course, you'll get 9.83. And of course, once we use 9.81, that is an average. Let's say Earth is gravitational, because you know that the radius of the Earth will change, let's say, if we assume, let's say, somewhere from the equator to the poles, yeah? Because the radius is not the same, because Earth is not a perfect sphere, of course. Now, G depends on, we can say, so basically, we can say gravitational acceleration of objects or free-fall objects depend on what? Depends on the mass of the Earth, depends on the radius of the Earth. So if we want to find the gravitational acceleration of any objects on any planet, of course it depends on the mass of the planet, whether it is Earth, whether it is, let's say, Mars, Jupiter, whatever the planet is, depends on the mass of the planet and also the radius of the planet as well, not the mass of the object. So remember, it depends on the mass of the planet and the radius of the planet. It does not depend on the mass of the object. Don't forget. So we have a note, another note, which is also important. Earth's gravitational acceleration varies, like we've mentioned, from 9.78 to 9.83, of course, at the poles. Yeah. So if we take average, we will get something like 9.81 meter per second squared, because this is gravitational acceleration. Now we also have another question which is very important. It says, why the law of universal gravitation is considered as an example of the inverse square law. Why Earth's gravitational or universal gravitation is considered as an example of the inverse square law. So the answer would be, I think it would be pretty obvious now, okay, because the force varies as the inverse square of the separation. So it's just not like the force varies or changes with the distance when the distance changes, let's say. No, it is with the distance squared. Not just that, okay, because, and it is also the inverse of that, yeah? So it's not like directly proportional, it is inversely proportional, and of course, not just inverse, it is the inverse and the square of the distance. Okay, so of course you can see this is because the force of two masses decreases as the masses move further apart. Okay, we have a sample problem. Now it says, sample problem says what? It says find the distance of or between 0.3 kilogram billiard ball and a 0.4 kilogram billiard ball if the magnitude of the gravitational force between them is 8.92 times 10 to the power negative 11. So obviously what you're going to do is you need to write the two equations. Okay, let's bring the pen back. So here's what you're going to do, yeah? You have the given information. You can zoom out a little. So we know that gravitational force equals to what? Equals to, like we've mentioned before, G equal to mass, or m1 times m2 divided by the radius squared. The magnitude of the gravitational force is given, yeah, which is basically, what does it say? It says find what? Find the distance between the two, so the force is already given. So if you're willing to find the distance, can I swap these two together? You can use cross multiplication, or radius squared, let's say, equals to what? Equals to g m1 m2 over fg, correct? And then of course, we don't want the distance squared, we want the distance, yeah? So later on you can take the square root for that. Well, let me just take this. So r equals to the square root of g m1 m2 divided by fg, of course. What is universal gravitational constant? That is, of course, 6.673 times 10 to the power negative 11. We've mentioned this. The first mass is 0.3. The second mass is 0.4 divided by the gravitational force between the two, and then once you do all this, of course, take the square root, then you will find out that the radius will equal to what? 3 times 10 to the power negative 1 meter, okay? Or you can say 0.3 meter. Okay, now we have another question, of course, says if the masses, let's see this, okay, all right, let me get a calculator. All right, it says what? If the mass of each ball in the sample problem 11, or the previous one, is 0.8 kilogram, at what distance between the balls will the gravitational force between the balls have the same magnitude as in the sample problem, let's say triple I, that was I, not 11. How does 1I, I thought it is, okay, triple I. So how does the change in mass affect the magnitude of the gravitational force? So if we assume that the mass of each one of these two is 0.8, then what will happen? Of course, the force between them is still 9.8.92 times 10 to the power negative 11. So find the radius. Now you can see here the radius becomes what? Becomes 0.692 meter, of course. So what can we say about the two? Yeah, the first one was 0.3. Now you can see the distance between the two will be bigger in this case. Why? Because remember, the bigger the mass, okay, the bigger the force of gravity. But since the force doesn't change, and let's say the mass have changed, so of course now the distance will be larger in this case. So we can say this: by increasing the masses, the force of gravity between them increased. Why? Because remember, these are directly proportional. The bigger the masses, the bigger the force of gravity. But, or you can say, but if we increase the distance, the force will decrease. Okay, so to keep the force, the separation between them must be increased. Now, we have also, remember, sometimes two force of gravity is given, and of course, a distance is given, and then they will ask you for another distance. Let's say there are two objects that are separated by a distance, a certain distance, okay? Then the force of gravity between them has a certain value. So what happens if we move the two objects further apart? Of course, then the distance between the two, let's say, will change, yeah? Or we can find the distance between the two when the forces are kept the same, or even when the forces change. So if two forces and two radii are given, radii would be the distance, the separation between them, radii, and one of them is unknown, like one of these, then of course we can use this equation to find, let's say, to find whichever that is unknown. So one example for that, we can say two masses which are 10 centimeter apart, yeah, attract each other with a gravitational force of 10 times 10 to the power negative 11 Newton. If they are moved to a distance of 5 centimeter apart, how much force will they exert on one another? That is, of course, you can see it is one of the national exam questions, or you can say WSATI questions. Okay, so let's solve, or try to solve this one and see which one is the correct answer. All right, so let's see. Let's, yes, change color. All right, so remember what we have, okay? It says two small masses which are 10 centimeter apart. So we can say, using this equation, Fg2 over Fg1, and of course we have what? Yes, you can see that we have radius 1, or the separation, the distance between them, squared, and then this is for the first time. Of course, these are, you can see, now you can cross multiply them, or whichever is unknown, you can find it using this equation. So now, substitute the numbers. So 10 centimeter apart, we can say, so R would be 10 centimeter, that is 10 squared, with a gravitational force. The gravitational force is 10 to the power, or 10 times 10 to the power negative 11, if they are moved at a distance of 5 centimeter, yeah? So the first one is 10, the second one is 5 centimeter. Remember, Mr., can I change, let's say, the centimeter to meter and then convert it? Yes. Can I can I use the numbers without changing the centimeter to meter? That is also yes, because centimeter and centimeter will cancel each other out. Okay, and then how large the force will they exert on one another? So what is going to be the force of gravity? So now here, you can use cross multiplication, of course, 5g, of course, multiplied by this, or here, I'll just multiply this, okay? You could just multiply this one to the other side, of course, you can find Fg, because Fg in this case will be the subject, yes? So we can say Fg equals to 10 squared multiplied by 10, okay? Times 10 to the power negative 11 divided by what? Divided by 5. So use a calculator, okay? 10 multiplied, or we can say 1,000 in this case, okay? Multiplied by 10 to the power negative 11. And then divided by 5. What did we do wrong? Okay, I think I've done something wrong. So, no. Okay, yeah, this is r squared, guys. Don't forget, this is almost, I didn't get a correct answer. That is because this is square and I didn't do the square. So, 10, I did not do this square either. 10 times 10 squared, that is 100. So that is 1,000. 1,000 multiplied by 10 to the power 10 to the power negative 11. I think this calculator is not working very well. All right, and then divided by 5 squared, yeah? And of course, the answer is going to be 4 times, the answer will be 4 times 10 to the power negative 10. But you see here, what is given is 40, don't forget, guys. So if you're going to add 1 0 here, you will have to add a decimal to this. So in this case, it's going to be negative 11. Okay, so this would be, or D, option D would be the correct answer here. Okay, now let's take a look at this question here, and then equals to 240.43. All right, now of course we have some past questions we can say, or national Wzari questions. It says G is what? Is a form of, let's say, universal law of gravitation. Which of the following are used to find G? Is a form from universal law of gravitation. So which of the following formulas are used to find G? Of course, if you make G the subject, which one of these do you think would be the correct answer? Can we say it is this? Okay. We would have, if there was an r squared, yeah, but you know that there is no r squared here, so of course it's not this. What about this one? Can we say it is this? Okay. What do you say? Is it? No, because that is, you could say reversed. Let's use this one here. So Fg equals to G capital M1 M2 over the radius square. So if you want to make this one the subject, you'll have to move this one down and move this one up. That is a cross multiplication, which I believe you guys know this already. So it becomes Fg multiplied by the radius squared and then divided by M1 M2. So this is M2, not M squared. So which one of these would be the correct option in this case, which is option C, correct? Okay, can we choose the last option D? No, because G is not squared in here. What about the second question? It says the value of G in the equation Fg equal to this is equal to what? We've mentioned before that the value of G equal to 6.63 times 10 to the power negative 11, of course, Newton meter squared kilogram over kilogram squared. And then the third one, or the last one here, for this lesson, we can say G in the equation F equal to this is called what? Is it called constant of universal gravitation? Is it called coefficient of friction? Is it called gravitational force or free fall acceleration? And the correct option is constant of universal gravitation. All right, so next time we'll talk about this hint, of course, which is very, very important. Then we'll proceed with some examples maybe, and then we'll continue with the rest of the questions. So until next lesson, guys, keep practicing, and I'll see you next lesson. Have a great day.